For over half a century, accessing outer space was restricted by staggering financial costs. Traditional expendable rockets cost up to $54,000 per kilogram placed into orbit. Breaking this economic monopoly required a fundamental shift in propulsion engineering. High-efficiency, fully reusable rocket engines capable of rapid flight turnarounds. $54,000 per kilogram. That was the brutal price of reaching orbit for most of the space age. Every gram mattered, every launch was a national gamble. To open the space frontier to commerce and industry, the world needed engines that could fly again and again, cheaply and safely, like aircraft. Enter AstroBase Space Technologies, a Bengaluru-based aerospace startup founded in 2024. Combining private technology capital with ISRO propulsion engineering expertise, AstroBase set out to build India's first medium-lift reusable orbital rocket family from the ground up, starting with its core propulsion heartbeat, the Everest engine. AstroBase was founded by Neeraj Khandelwal and Divakumar Thamisidi, two propulsion engineers who spent years inside India's public space program. They understood that a nation's future in orbit would not be decided by its biggest rocket, but by its most efficient one. So they raised private capital and began building from first principles. The ambition is audacious. Build India's first medium-lift, fully reusable orbital rocket family from a clean sheet of paper. Not a single mission, but an entire launch system engineered for rapid reuse. And at the heart of that system lies the component that makes it all possible, the Everest engine. Every rocket engine is a machine built to lift hundreds of tons of propellant against gravity. Liquid fuel and oxidizer are driven into a combustion chamber at enormous pressure, ignited, and ejected through a nozzle at supersonic speed. The pumps that force these fluids in are called turbopumps, and they are the true heart of the machine. To understand the leap AstroBase is making, we must examine engine thermodynamics. Heritage gas generator engines like ISRO's Vikas burn a portion of propellant in a preburner to spin the turbopump, dumping the unburnt exhaust overboard. This results in significant enthalpy loss and limits chamber pressure to around 58 bar. Engineers soon developed a better architecture, staged combustion. Instead of dumping the preburner exhaust, its hot gas is routed directly into the main chamber. Closing the loop recovers nearly all of the propellant's energy and pushes chamber pressures toward 200 bar and beyond. The idea of full-flow staged combustion is older than India's space program itself. Soviet engineers explored the concept in the 1960s, and SpaceX's Raptor finally carried it into flight. Now, AstroBase is racing to make India the fourth nation to master this demanding cycle. Full-flow staged combustion changes everything. Everest routes both liquid methane and liquid oxygen through separate preburners. Both streams enter the main combustion chamber fully gasified. Because zero gas is dumped overboard, the engine achieves near 100% propellant efficiency while driving chamber pressure past 300 bar. The rocket equation ties every launch together. The change in velocity equals exhaust velocity multiplied by the natural logarithm of the mass ratio. Higher engine efficiency means less propellant and more payload, and every point of efficiency translates directly into kilograms of cargo and millions of dollars saved per flight. Full-flow staged combustion represents the summit of thermodynamic engineering. Because both propellant streams arrive at the chamber fully gasified, Everest can throttle deeply, from 50 to 110% of rated thrust. That enormous operating range is the secret behind controlled, survivable vertical landings. Let's tear down the Everest engine. High-pressure liquid oxygen and methane feed twin preburners. The gasified propellants power separate turbopumps before mixing in the main chamber. Monolithic regenerative cooling channels withstand intense heat, while hydrostatic bearings eliminate mechanical contact and wear. Inside Everest, High-speed turbopumps spin on hydrostatic bearings, suspended by fluid pressure instead of mechanical contact. Propellant valves open and close with millisecond precision, while an engine controller orchestrates every cycle. Monolithic cooling channels shield the chamber from combustion gases hotter than 3,000 Kelvin. Starting an FFSC engine is a carefully choreographed dance. Valves open in sequence, turbines spin up, and combustion lights in a matter of microseconds. A single mistimed command could destroy the engine in seconds, so the startup sequence is simulated and rehearsed thousands of times before it is ever allowed to fly. Building an FFSC engine requires advanced metallurgy. At AstroBase's 46,000 square foot Bengaluru plant, industrial metal 3D printers use selective laser melting to print copper-nickel superalloy combustion chambers. This eliminates hundreds of welds and brazed joints, dramatically improving structural reliability. The choice of material is as important as the printing process itself. Copper-nickel superalloys combine high thermal conductivity with remarkable strength at extreme temperatures. This lets coolant channels strip heat away faster than the fire can add it, keeping the chamber wall intact through continuous 300-bar operation. Every printed component must prove itself before it earns a place on a flight engine. Parts are laser scanned, X-rayed, and hydrostatically pressure tested. AstroBase's 46,000 square foot Bengaluru plant was designed so that printing, inspection, and assembly all happen under one roof. Everest burns liquid oxygen and liquid methane. Unlike traditional kerosene engines that leave heavy carbon soot deposits inside turbopump channels, methane burns cleanly. This lack of coking enables rapid turnaround times without requiring tedious engine refurbishment between launches. At -183 degrees Celsius, oxygen is a pale blue liquid. At -161 degrees, methane boils into a fluid that packs more energy per kilogram than kerosene. Storing and pumping these cryogenic liquids at launch scale is one of the hardest problems in modern engineering. Methane also self-cleans. Because it burns without soot, an Everest engine does not need to be stripped down after every flight. That simple chemical property is what makes rapid reuse economical, transforming a rocket engine from a disposable expense into a reusable asset. Comparing global propulsion specs. With Everest, India becomes one of only 4 nations alongside the United States, Russia, and China to build an operational full-flow staged combustion engine class, putting AstroBase in an elite international aerospace league. Engineers test hardware at AstroBase's private 21.5-acre cryogenic test facility in Anantapur, Andhra Pradesh. Supported by in-space authorization, subscale hot fire tests and powerhead validations pave the way for full-scale vacuum hot fire tests. Testing proceeds in stages of increasing violence. Engineers begin with powerhead firings, advance to subscale hot fires, and finish with full-scale engine tests. Every firing feeds thousands of channels of data back to the control room, revealing how the engine breathes, vibrates, and burns. Every component must survive longer than the mission demands, and every engine must demonstrate reliability through repeated firings. Certification is not glamorous work, but it is the wall that separates a demonstration from a flight-proven propulsion system. A cluster of Everest engines will power AstroBase's 2-stage reusable launch vehicle. Designed to lift 3 to 10 tons into low Earth orbit, the first stage utilizes grid fins and dynamic engine throttling from 50 to 110% to perform precision retropropulsive landings. After stage separation, the booster flips and falls back toward Earth, using aerodynamic grid fins to steer through the upper atmosphere. As it approaches the landing zone, Everest's deep throttling slows the vehicle from supersonic to a gentle hover before it touches down on its own landing legs. Reuse transforms the economics of spaceflight. A vehicle that can fly week after week pushes the cost of launch toward a fraction of today's price. That opens markets that were previously locked out of orbit entirely, from fresh food delivery to orbital manufacturing. With a 4-meter payload fairing, AstroBase's launch vehicle is tailored for deploying high-density satellite constellations. Low launch costs enable commercial satellite operators to deploy broadband, Earth observation, and defense hardware at unprecedented frequency. AstroBase's 4-meter fairing is designed to carry the next generation of space infrastructure: broadband megaconstellations, Earth observation fleets, and defense payloads. More launches mean more capacity, more resilience, and more data flowing down to users on the ground. AstroBase does not fly alone. Skyroot has delivered orbital launches with its Vikram rocket, while Agnikul pursues booster recovery and advanced propulsion. Together, these companies are building a complete private launch supply chain on Indian soil. Government policy accelerated the boom. In-Space opened the country's launch infrastructure to private players, and venture capital flooded into the sector. Startups now collaborate with ISRO instead of waiting for it, a partnership that has supercharged India's ambitions. Driven by Skyroot's orbital launches, Agnikul's booster recovery programs, and AstroBase's breakthrough FFSC propulsion, India's private space ecosystem is expanding rapidly. Supported by government policy and private capital, India's space economy is accelerating towards a $45 billion valuation by 2030. The road ahead is measured in milestones: first subscale firings, first full-scale hot fire, first booster static test, and finally, first flight. Each is a checkpoint on the path from an audacious idea to a working, reusable launch system. An operational full-flow staged combustion engine would place India alongside the United States, Russia, and China as only the fourth nation to master the technology. It is a leap in engineering capability and a statement about the kind of future India intends to build. From $54,000 a kilogram to a reusable engine on a reusable rocket, the story of Everest is the story of an industry being rewritten. The frontier is no longer the luxury of a few nations. It is a frontier open to every engineer who dares to reach it. AstroBase is not building a single rocket. It is building a manufacturing economy for orbit, where engines are printed, tested, flown, and landed with the rhythm of an assembly line. If Everest reaches the pad on schedule, India does not just join the club of nations that can orbit heavy payloads. It redefines how cheaply that club can operate. And when the first Everest engine roars to life above Anantapur, every other engine project on Earth will have to ask the same question it does. What could we build if we had no fear of gravity?